Bismillahirrahmanirrahim. Today we will discuss matrix of a tensor with respect to principal directions. That how can we write a matrix with respect to matrix of tensor with respect to principal directions. As you have studied that if you have a tensor T with respect to basis EI, then you can write that tensor with respect to basis EI dash if the transformation matrix Q which transforms EI to EI dash is given. In similar way we can write matrix of tensor T with respect to principal directions. Let's see how can we do that. We know that for a real symmetric tensor there always exist three principal directions which are mutually perpendicular. We have discussed this thing in our previous lecture, that for any real symmetric tensor we must have at least three principal directions which are mutually perpendicular. Let us suppose that n1, n2 and n3 be unit vectors in these directions. That we are taking three unit vectors in these directions. Then we can use these n1, n2, n3 as base vectors. Then by using these n1, n2, n3 as base vectors, we can write this components of tensor T with respect to these n1, n2, n3, these base vectors. T11 equals to n1 dot tn1. This is written with the help of this. We know that components of tensor T with respect to basis EI can be written with this Tij equals to EI dot Tej. So here we have n1, n2, n3 instead of E1, E2 and E3. So T11 equals to n1 dot tn1. Now n1 dot tn1 equals to lambda 1 n1, because we know that for principal directions there are eigenvalues lambda 1, lambda 2, lambda 3. Lambda 1 for first principal directions, lambda 2 for second, and lambda 3 for third. And we are taking n1, n2 and n3 parallel to these directions, as we have written here, n1, n2, n3 be unit vectors in these directions. So we can write tn1 lambda 1 n1. This is exactly the same when we have started eigenvectors, in which we have written that A is eigenvector with eigenvalue lambda, Ta is equal to lambda A, any vector parallel to A, where we have said alpha A, any vector parallel to A is an eigenvector with same eigenvalue, and we have proved there. We have shown that T of alpha A equals to lambda times alpha A. From there we have written this lambda 1 tn1 equals to lambda 1 n1. So we can write lambda 1 n1 dot n1 dot n1 equals to unit vectors 1, so t1 equals to lambda 1, and t22 n2 dot lambda 2 n2 lambda 2 and 2 dot and 2 lambda 2 and 2 dot and 2 1 t3 lambda 3. And now for t12 equals to n1 dot tn2, so this would be lambda 2 n1 dot n2. This is 0 n1 dot n2 because we are taking n1 n2 and n3 in the direction of the principal direction, parallel to principal directions, and we know that principal directions are orthogonal with each other, so it means that these are also orthogonal with each other. So n1 dot n2 equals to 0, so t12 equals to 0 and t21 0. Similarly t13 and 1 dot and 3 0, t23 and 2 and 2 dot and 3 0, so t23 is equal to 0. Now we can write this tensor, any tensor t with respect to principal directions n1 n2 and 3 as t11 t22 t33. all others are 0. We have seen here that all they are 0. So this matrix is diagonal and the diagonal elements are the eigenvalues of t. It means that if we want to write any tensor t with respect to principal directions, then result is simply this. The result is a diagonal matrix with diagonal elements are eigenvalues of tensor t, lambda 1 lambda 2 lambda 3. Now we will apply this on an example. We have given this tensor t and you can see that this is real and symmetric, so it would have at least 3 principal directions which are orthogonal. If we denote these principal directions with n1 n2 n3, then write this. What does this mean? This means that you have to write this tensor t with respect to these principal directions. So to find the principal values, we have this characteristic equation. Lambda cube minus 7 lambda square plus 14 lambda minus 8 is equal to 0. By solving this, we have eigenvalues lambda 1 is equal to 1, lambda 2 is equal to lambda 3 is equal to 4. These are principal values of tensor t. Now we will find corresponding principal directions. For lambda 1, here we are again we are making the use of equation number 4 on page 34. 3 minus 1 into alpha 1 minus 1, t12 is minus 1, t13 0, so it will be 0. Here t21 is minus 1 and t22 3. 3 minus 1 to alpha 2 plus t23 0. This is 0, this is 0 plus 1 minus 1, t33 minus 1 and t33 is 1, so 1 minus 1 into alpha 3 is equal to 0. Now from this last equation of this system, we can see that our alpha 3 is arbitrary, that we have 0 times alpha 3 is equal to 0, so the system will be satisfied for all values of alpha 3. So it means that our alpha 3 is arbitrary. Now from these two equations, we have this 2 alpha 1 minus alpha 2 equals to 0, minus alpha 1 plus 2 alpha 2 is equal to 0. And we can see that this is a homogeneous system of 2 two equations, and its determinant is not equal to 0. 4 plus 1 equals to 5. So this system has only trivial solution, which is alpha 1 alpha 2 equals to 0. So we can write from this equation alpha 1 square plus alpha 2 square plus alpha 3 square is equal to 1. Alpha 1 alpha 2 they are 0, so we are left with only alpha 3 is equal to plus minus 1. So first principal direction is n1 equals to plus minus e3. This is the unit eigenvector in principal directions, in one of principal directions, as we have said in the theory. We have to find 3 vectors in these directions. This is 1 corresponding to eigenvalue 1, lambda 1 is equal to 1. Now lambda 2 is equal to 2. Three minus 2, alpha 1 minus alpha 2 plus 0 is equal to 0, minus alpha 1 plus 3 minus 2 into alpha 2 plus 0 times alpha 3 is equal to 0. 0 plus 0 into 1 minus 2 alpha 3 is equal to 0. From here we can see that our alpha 3 is 0, and from above two equations, this and this, we have alpha 1 minus alpha 2 is equal to 0, alpha 1 minus alpha 2 is equal to 0. This is homogeneous system and its determinant is 0, so it will have infinitely many solutions. So we can write alpha 1 equals to alpha 2. So from this equation we can have as alpha 3 equals to 0, so we can write alpha 1 square plus, instead of alpha 2 we are using alpha 1, so 2 times alpha 1 square is equal to 0. So we can write alpha 1 plus minus 1 over square root of 2. So alpha is, it will be also be equal to alpha 2, because alpha 1 and alpha 2 they are equal. So second unit vector is n2 plus minus 1 under 2 plus minus 1 under 2. So for lambda 3 is equal to 4, we have this first equation, then second, fourth, again from this system, and its third equation will give us alpha 3 equals to 0. Now from first two we have this, and we can write alpha 1 equals to minus time alpha 2. So from this equation again alpha 1 is equal to plus minus 1 over square root of 2, but alpha 2 is minus plus 1 over square root of 2. It means that if alpha 1 is positive, then alpha 2 will be negative, because their sign is opposite. They are equal but with opposite sign. So if alpha 1 is minus, then alpha 2 will be plus. So that is why we are writing minus plus. So third is n3. This is these are 3 n1, n2, n3 unit vectors in the direction in these directions. Which directions? Principal directions. As we have done from our starting lecture, from where we have started our lecture. n1, n2, n3 unit vectors in these directions. We have calculated n1, n2, n3 in these directions. This is n1, this is n2, and this is n3. Oh, this is Q. This is the transformation matrix and this matrix is transforming a E1, E2, E3 bases into N1, N2, N3 bases. And this is orthogonal QQ transposes identity, and this is orthogonality condition. This must be satisfied. You can check from here, and if I is 1, we have QP1, QQ1. So we will open the summation. Sorry, if suppose PQ is 1 1, so delta 1 1, and right hand side we have 1, so we must have 1 on left hand side. Q1I, Q1I. We will open summation on this I because I is dummy. Q11, Q11 plus Q12, Q12, Q12 square plus Q1, Q31, Q31, Q31 square. This is Q11 square plus Q21 square plus Q31 square. Q110, Q210, and Q33 is plus 1. So left hand side is also plus 1. So no, if P is not equal to Q, say P is 1 and Q is 2, so delta P12, delta P1, sorry, delta 12, delta 12 is 0, so left hand side must be equal to 0. 1, 2. This will be Q11, Q21, Q11, Q21 plus Q12, Q22, Q12, Q22, 1 over 2, 1 over 2, Q13, Q23 plus and minus 1 over 0 plus 1 over 2 minus 1 over 2. So this will give us 0 on left hand side. So this condition will be satisfied for all PQ. Simply you can use this formula to write tensor T with respect to these bases N1, N2, N3. Here will be transpose of Q. Here this T which is given, again Q, and when you multiply all these three you will have this 1 0 0 0 2 0 0 0 4. You can also write directly because you have proved in the theory that if N1, N2, N3 are in the direction of principal direction, as we have said, N1, N2, N3 unit vectors in these directions, principal directions, then tensor T with respect to these N1, N2, N3 will be a diagonal matrix with diagonal entries. Will diagonal entries contain the eigenvalues of tensor T? Lambda 1 is equal to 1, lambda 2 is equal to, and lambda 3 is equal to 4. You can write directly or with the help of this Q, which relates N1, N2, N3 with E1, E2 and E3. Now these are three questions from exercise 2b4 to 2b40 to 2b41 to b42. In these three questions, tensor will be given, and what you have to do, you have to find principal values and principal directions, and then write the given tensor T with respect to these principal directions. Similarly, as we have done in this example, you have to simply follow this example and do the exercise. Today lecture is very simple. I hope you will understand this easily. Thank you so much. Allah Hafiz.